I have you loud and clear.
Hello. Welcome. Science.
And that is to say,
physics,
medicine,
nature,
or
Space. Time.
the brain,
Life. The universe.
Hello, welcome to The Naked Scientists, the show where we bring you the latest breakthroughs in science and technology with me, Chris Smith, and with Izzy Clark.
This week, we're sorting through recycling and how it works. What happens to the stuff you put in your recycling bin, and is the system actually working?
And in the news, the artificial leaf that turns CO2 into fuel and how to stop cybercrime.
The Naked Scientists podcast is powered by ukfast.co.uk.
Now, first up, with winter approaching, here's a piece of good news. A new experimental drug that can knock out flu and other viruses has been developed by scientists in America. Called EIDD 2018, it works by mimicking one of the letters that makes up the virus's genetic code.
When the virus grows, it accidentally uses the drug molecule instead of its own genetic letter, introducing genetic spelling mistakes that are lethal for the virus. Cambridge University's AJ Veldhuis, who studies how viruses grow but wasn't involved in the present research, took Chris through what the US team have done.
Flu is a massive problem for human health and also for our economy. We have vaccines, but they're only 20 to 60% effective, and the virus still kills a lot of elderly and young people every year. We have some antivirals, but the virus is constantly getting resistant to them, so we need a new drug that can help us fight a new pandemic.
And some of these antiviral drugs are not actually that good, are they? They're not the viral equivalent of when you give penicillin to someone with meningitis and save their lives. These drugs, they work a bit, but they're not brilliant.
Exactly, they're not very effective, and as I said, the virus can get quite easily resistant to them, and then their efficacy is completely gone. This group has been looking to find a nucleotide analog. So the viral genome consists of nucleotides. They have names, and usually they're abbreviated as A, G, C, and U.
These are genetic letters.
These are indeed genetic letters. And the drug mimics the C letter. The virus can incorporate that into its genome. This results into a mutation, and this can lead to misfolding of viral proteins or even completely not working proteins.
I get it. So you would give cells that are infected with the flu this molecule, and when the virus is making copies of its genetic information, it mistakes this one that's the drug for the chemical it should be putting in, and it messes up the sequence of the viral genetic information.
That is correct.
How have they tested it so far?
So they've tested it in a number of ways. What the scientists first did was add the drug to cells growing in a petri dish. Normally the virus would kill these cells, but in the presence of the drug it wasn't able to. The cells were basically healthy and cured. Next, they moved to animal experiments, ferrets, that they also gave the drug to. Normally, when these ferrets get infected with the virus, they develop fever, start coughing, sneezing. But in the presence of the drug, the fever disappeared much more quickly, and they didn't have as much virus particles in their airway system.
And critically, were the animals harmed by the drug? Because one's always very worried about side effects. All drugs have side effects.
They didn't see evidence for this. The cells remained healthy in the presence of the drug for a very long time.
One of the issues with treating the flu is that the viruses evolved to become resistant to drugs in the same way that bacteria evolved to become resistant to antibiotics. Did that happen here? Did the tests on the cells in the dish or on the ferrets actually produce any viruses that were resistant?
So that's a very good question. There is evidence that influenza can get resistant to drugs like this new one. So they did specific experiments to test this. They added virus to cells containing the drug and looked for resistance mutations. And they didn't find any. So that is very, very promising.
Do we know why?
It could be that it is very difficult for the virus to make a resistant mutation. Maybe it needs to mutate at a couple of sites at the same time to be able to cope with the drug. And that just takes time, and that wasn't seen or mimicked in this experiment.
Why is the virus fooled by this drug that it accidentally shoves into its genetic information, and our own cells, which also have genetic information on them using similar chemicals, aren't?
This drug is incorporated by an enzyme called a polymerase. And all cells and all viruses have polymerases, but they're all slightly different. And it seems that this drug just binds better to the flu polymerase than to a human one.
And do you think that the differences that they saw in the ferrets would actually be clinically significant? So if that were a patient and a patient responded the same way the ferrets did, that actually this would translate into a real benefit clinically?
So in their experiments, they took along a control, and that control is currently available over the counter. It's Tamiflu. And what they saw in the ferret experiments was that their drug works better at reducing fever and minimizing clinical symptoms than Tamiflu. So that is very promising.
One of the attractions of Tamiflu is you can pop a pill. You don't have to inject this stuff. Is it the same for this drug, or would this be an injection?
In theory, this could also be provided in the form of a pill.
And cheap, easy to make?
That I don't know.
That's a question of wait and see then.
Exactly. Although I would predict that this could be cheaply made. It's a small molecule, so it could be scaled up quite easily.
Thanks to AJ Veldhuis, who was commenting on results presented in the journal Science Translational Medicine by Richard Plemper and his team.
And what's doubly exciting about that drug is that, and admittedly it is early days, it also seems to be active against other viruses as well, including some that cause colds. So you never know, Izzy, there might be a cure for the common cold on the way.
Oh, that would be so good. And from colds on to all things hot, climate change. And one of the challenges we face is not just how to reduce carbon emissions, but how to scavenge back some of the carbon we've already put into the atmosphere, ideally without compromising our standards of living.
And this week, scientists at the University of Cambridge have unveiled a technology that might help us to achieve both of those aims. This is an artificial leaf that, like the real leaves used by plants, takes in light and uses it to turn carbon dioxide into a useful fuel. In this case, it's a mixture of carbon monoxide and hydrogen. We call this syngas. And Katie Haler went to see it in action with its inventor, Erwin Reisner.
We have demonstrated that we can convert the greenhouse gas carbon dioxide together with water into an energy carrier, which is known as syngas. Syngas is a gas mixture made out of carbon monoxide and hydrogen, currently used for methanol synthesis, for example. You also extract the hydrogen from syngas to make fertilizers. We are excited about syngas because syngas can be converted to liquid carbon-based fuels, essentially gasoline.
Let's take a closer look then. So on the desk in front of us is a box. Is that plastic? It's transparent in nature, and then there's lots of nuts and bolts and things going on. Separately, you've got a little square with some wires coming out of it. Can you explain what is happening step by step?
Absolutely. So inside the box we have this artificial leaf, which means these are the electrodes, and the electrodes now take up the light, and this energy from the light is then being used to drive our catalysts.
Is the light being absorbed? What's going on? What materials are we talking about?
Yes, it's being absorbed by semiconductors. A semiconductor can absorb light. In our case, the semiconductor, rather than producing electricity, we use the energy to drive a catalyst to make syngas.
It's been described as an artificial leaf, and on the cycle over here, couldn't help but pick up this beautiful green autumnal leaf in front of me. How does this relate to what you're doing?
We try to adapt the concepts from photosynthesis, and in our case, we also have a leaf configuration, so it's quite a thin platelet, if you like, known as an electrode. And here we also take the carbon dioxide, but we do not produce sugars. We want to produce gaseous or liquid products.
So you've got a box which has carbon dioxide pumped into it through some water or an aqueous solution. Then you've got your quote-unquote leaf, has got some semiconductors in it which absorb the light, do some clever chemistry with the light on some catalysts in the leaf, and that is how we get the syngas.
That's correct. And it's really the choice of all these materials and the combination that make this a functional system.
What about a cloudy day? What about winter in the UK?
So one of the strengths of this system is that it does not rely on very strong or high light intensities. It can also operate under cloudy days or even under winter, so in quite low light intensity situations.
Now, why hasn't this been done before? What are the current technological or scientific barriers?
The artificial leaf contains a very large variety of different elements, very unproblematic elements, but it also contains a range of problematic or poisonous or rare elements. This would, for example, be lead or silver.
Okay, so would the idea be to swap those out?
Yes, that's what we will do in the next stage. So we know precisely which layers to replace into substitutes, and we will look for replacements.
And once we've got the syngas, how do you go from that to fuel? How green is that process?
So this process is established. It's known as the Fischer-Tropsch process. And with certain high temperature and catalysts, you can convert the syngas into the liquid fuel. This is something we can in principle also do sustainably.
Is it scalable?
We hope so. So there are many limitations at the moment. The stability is not high enough and also the efficiency is not high enough. But we hope with further development we can improve on these.
How would you see this kind of technology being used?
We see there's still a lot of challenges ahead. We cannot promise that this will be implemented in a couple of years. We recognize for real commercial application there are probably decades of development needed. But I think there are many possibilities. One way would be to use it on very large scale for centralized energy production. But there's also a possibility for off-grid or localized uses. So I don't see a reason why this cannot be a smaller scale device that generates energy where there's no grid.
Be amazing if they can make it work, won't it? Erwin Weissner, and he was taking a leaf out of how plants photosynthesize to turn CO2 into a fuel. The work that he was demonstrating for Katie was published in the journal Nature Materials. Well, over to sport now. Everyone's mind is focused because of the rugby, of course. Come on, England. It turns out that if you become a professional footballer, then your risk of Alzheimer's disease goes up 5 times. That is, unless you play in goal, which seems to be a little bit safer. Now, these are the results from a new study by Glasgow University's Willie Stewart. So, how did he and his team discover this, and why might it happen?
To do this properly, you really need a large cohort of people to look at. So you need a large study population. So we looked at a study population of just over 7,000 former professional Scottish football players. And we compared them to people in the community who were as near as we could make them. So they were born in the same year, they lived in the same postcode areas, but they'd never played professional football. And we dug into their health records to see how they were dying.
And what trends emerged?
The headline is that people who participated in professional football were more likely to die of neurodegenerative diseases and dementia, about 3.5 times greater risk. As well as that risk of neurodegenerative disease, we saw that other health measures looked better. So they had less cardiovascular disease, less death through some cancers. And that resulted in a small lengthening of lifespan. So our footballers were living for about 3 years longer.
And it wasn't just because they were living longer that they were succumbing to the dementia. Were they getting the dementia at an earlier age than one would anticipate, or were they at least getting the dementia when other people who are equivalent to them but not footballers were not getting dementia?
That's a very valid point. That was one of the first questions we asked, because here we're seeing our footballers doing better, living longer. So maybe all we were reflecting was that older age population where dementias come in. So what we could do, because we had a properly set up study with lots of individuals to look at, we factored into it the benefits they were getting in cardiac disease and cancer. So we could factor those in. Adjusting for that, they still had 3.5 times a higher risk of death through neurodegenerative disease.
And was it right across the spectrum of neurodegenerative diseases? Because that term can embrace a large range of pathologies, can't it?
Exactly. That's a headline, dying of neurodegenerative disease. We looked beneath that to people who were dying with. So the way the death certificates are written, they have on the top line the actual direct cause of death. And so that may be a heart attack, say. And then beneath that, the doctor will also record other diseases and conditions that were there at the end but may not have contributed to death. And that's where things like Alzheimer's disease may appear. So using that, we could look in more detail at individual diseases. And when we did that, what we found is that Alzheimer's disease risk was the highest. Footballers were more likely to die with Alzheimer's disease, up to a factor of 5 times more likely. And then motor neuron disease, which is a rare condition, but nevertheless, we saw about 4 times as often in our former footballers, down to Parkinson's disease, where there was a doubling of risk.
Does it matter where on the pitch someone plays? Because arguably some positions, they're going to get exposed to more head injuries than others.
Yeah, we looked at outfield players against our goalkeepers. Our goalkeepers had a less than half as likelihood of getting drugs for dementia.
I know it wasn't part of the scope of this study, which was very much observing relationships between 2 different groups of people. But why do you think people who play in these certain positions or play these sports are at these exaggerated risks of getting these sorts of conditions?
That's the challenge now, is to try and identify what it is about the brain injury event that somehow changes the brain. There's a number of things that we're recognising now that happen at the instant of injury. So, for instance, the blood-brain barrier can break down at the time of injury and can persist for some time. We see inflammatory changes in the brain that can happen in some of these individuals and can persist for some time. And we also see that the white matter, the fine fibre tracts that run from the brain cells, can become stretched and damaged and broken, and that again can persist and evolve over some time. So there's a few candidates that we can work with, but at the moment we don't have, if you like, the smoking gun, the one thing that we can say this is what happens and this is what we're chasing now.
Can you say, though, what would be the best way to mitigate this? Is it just to say to people, we've got to ban heading of the ball? Because the Football Association or representatives of that movement have said, oh, well, we're going to have special monitoring for people who have a concussion or have a head injury on the pitch. But from what you've been saying, by then the horse has bolted, hasn't it? It's too late. They've already sustained what could be eventually a life-changing injury when they're older.
So, I mean, I think it's important to say that one concussion, one mild brain injury, we haven't got evidence yet would be a risk later in life. So it's still okay to bang your head and not worry too much about dementia. That's important. But it's the cumulative effects. And so while we may take years to figure out what the pathology is that's driving this, I think there's enough in the evidence from our recent publication and work going back several years to say, can we do something to reduce the cumulative small impacts that may not even cause any significant injury that we can detect? So can we cut back a bit on things like training for heading during the week? Do we need to do it as often as we do now? Do we need to do it as many times in a week as we do now? So is there ways of just making those changes that could be the difference in the long run?
Interesting, isn't it? Willie Stewart there, he's from the University of Glasgow. The study showing that link between brain diseases and professional football was published this week in the New England Journal of Medicine.
Hiya, I'm Phil Sansom, and I host the Naked Genetics podcast. Genetics is huge right now, from those home DNA testing kits to futuristic gene therapies to treat diseases. And if, like me, you're just trying to get a grip on what genes can and can't tell you, then this might be the show for you. Each month, we are telling scientific detective stories and shining a light in directions you might not expect, like gene sequencing a puppy.
Bruce, biscuit.
Or maybe tearing apart a flower.
Oh boy, you've taken all the parts off.
Well, that one I messed up. So that shows you how good he had to get at this.
And even drinking a bunch of gin.
That's very refreshing.
Don't miss out. Subscribe to Naked Genetics wherever you get your podcasts.
Still to come on The Naked Scientists, a spray-on treatment for plants that protects them from droughts, and we delve into the world of recycling. Meanwhile, the world of online gaming is huge among teenagers and is becoming a hotbed for cybercrime. One particular type of hack is a distributed denial of service, or DDoS attack, where a victim's internet connection is flooded with so much traffic that it shuts down. Gamers are increasingly using these attacks to gain an advantage by knocking their opponents offline.
But this activity is illegal, and it can be very disruptive for other innocent internet users who can often get caught in a crossfire. So Ben Collier from the University of Cambridge has been looking at what sorts of interventions actually work. Now, putting people in prison and stiff penalties don't actually seem to make very much difference, but taking down the computer networks that are used to do these sorts of attacks does work pretty well, but best of all is just a plain old simple tap on the shoulder with an online warning message to the people who are commissioning the attacks. And Adam Murphy heard why.
We've been looking at a particular type of cybercrime called DDoS. It's like, when you go to visit a music festival website, when the tickets open and everyone crashes the server because there's too many people going on. It's basically like that, but it's been weaponized as a form of cyber attack. So what we've done is we've used a bunch of detection techniques, looking at what the police are doing and seeing whether or not it works.
So how would you go about actually doing that to someone else's computer?
There's two ways you can do it. So the first one is called a reflection and amplification attack. That's where you look for computers on the internet that are poorly configured and you send them a signal. But when you send them the signal, you pretend to be the victim. So you send this signal to them. It's quite a small signal, doesn't take up much resources for you. And they send a very, very big signal back. But instead of sending it back to you, they send it back to the victim. The second way is using botnets. essentially infect other people's computers using computer viruses and get control of them, and then use these to send lots and lots of these signals and packets of information and overwhelm people's computers.
Why would you want to do that? So what are people looking for to use these for?
There's a range of different reasons why you might want to knock someone offline. So first, and one of the most common ones we see, is computer games. So if I'm playing an online computer game like Call of Duty or something, and I'm not very good at it, and my opponent's beating me a lot.
I can relate to that.
Yeah, me too. Then I might want to annoy them or get back at them by booting them off the internet. And then I would use this service to find out their IP address and then knock off their home connection, basically. But the problem is then you might knock off everyone else who's on, in their village or whatever that's on the same sort of set of servers, basically. There's some more sort of nasty stuff as well, although those are obviously serious too. So you might want to blackmail a business or another website, by saying, we'll take you offline unless you pay this much money. And then we get into the really serious stuff. So you can use this against infrastructure. For example, you could use it to take like a hospitals' public systems offline, any kind of public service or things like that has a public-facing IP address. You can use this to take it offline, basically.
Why do the interventions that work, so taking down the infrastructure and messaging people, why do those interventions work so well?
So for the infrastructure, we think that's because it's a very centralized market. So actually, there's around about 50 of these services, 50 or 60, doing any real number of attacks at any given time. But actually, there's a lot of reselling going on. So there's a small number of people, maybe 10 to a dozen, that are actually running most of the infrastructure, a small number of services, and they basically sell on to the other services their capacity. This means that if you take down the infrastructure, it causes a lot of knock-on effects for everyone else. And actually, the people that run the infrastructure, so the server managers, their job's really, really boring. So they're actually quite easy to dissuade. And when we saw this big FBI sting, actually, we saw lots of these server managers who the networks depend on say, yeah, I'm done. I'm not interested in this anymore. The messaging intervention's a bit more complicated. I think possibly the reason behind it is a kind of like digital guardianship sort of thing. One of the things people often say about cybercrime is that it's often difficult to know online what's legal and what isn't, or when you've crossed that boundary. And I think for a lot of these people, there's a lot of basically young kids doing this stuff who are doing this, but they don't really realize it's illegal. And actually in these communities, a lot of people will say, oh, it's not illegal, it's fine, the police don't care about this stuff. But I think if you're a 15-year-old kid and you're sort of searching for this stuff, these adverts hit you basically as soon as the thought's forming in your mind that you want to do it. Bear in mind the thing you're about to do that we can see you about to do because you're Googling it is illegal, just so you know. So it's kind of like a tap on the shoulder, basically saying, we're watching you. And we think so the timing and the targeted nature of the adverts is actually causing this effect.
Some very important work. That's Ben Collier there, and that work on cybercrime has just been presented at the ACM Internet Measurement Conference 2019.
And finally, from the cyber world to the real world now, the Earth's climate is predicted to heat up over the coming years, and that means droughts are also expected to become much more common. And droughts are a really big problem for farmers. At the moment, they're costing some $30 billion a year in lost revenue and lost crops and compensation. So can science help?
The answer is possibly, thanks to a new spray-on treatment called Opabactin that artificially activates a plant's natural drought response. The idea would be to use it to prepare plants before disaster strikes, making them more resilient when the worst happens. To find out how it works, Phil Sansom met up with Cambridge University plant scientist Jim Rowe, who wasn't part of the research but works on similar aspects of how plants grow.
So they've made a new chemical that activates the plant's own drought stress responses. When you spray the plants with this chemical, they stay greener for longer when you then stress them.
What is this chemical?
So actually what they did was they took an existing chemical that occurs in plants that's actually a plant hormone called abscisic acid, and they then looked at the molecule it binds to, which we call a receptor. They looked at lots of different chemicals and designed a new one that binds the receptor even more strongly than abscisic acid.
Oh, so it does something similar to something that actually exists in nature already?
Yeah. So we would call this a hormone analog. Plants normally under drought stress and stressful conditions will produce this hormone, abscisic acid, and this basically will tell the rest of the plant, water is scarce, we need to look after it and try and survive this.
Now, call me crazy. I knew animals had hormones. I didn't realize plants had hormones too.
Yeah, and they do a lot of similar things to animal hormones. So they might control the way that plants grow and develop. Stress responses such as drought or response to pathogens or response to being eaten.
Now tell me, how does abscisic acid work?
Abscisic acid is, we think, mostly made in the leaves. What it does is it will close the small holes in the leaves that are called stomata to help the plant lose less water in response to drought. It can also control the way that the plant grows and develops under stress. So, for instance, a small amount of abscisic acid will stop plant roots growing sideways and make them grow down to try and get to deeper water.
It just does loads of different things that help it when there's not much water.
Yeah, it has a whole plant effect and does lots of different things in lots of different places.
That's amazing.
Yeah, I think so too.
So does this new compound work in exactly the same way?
It's hitting the same receptors that abscisic acid is. It won't happen in exactly the same way, quite possibly, because there may be other signals that would normally happen in the case of a drought, but it's mostly activating the same response.
Are there any downsides for a plant if you give it all these like drought responses?
Yeah, there are. It takes quite a lot of resources and investment to protect yourself from these stresses. And so if you're shuttling all your resources to protection, you might get short and stunted plants.
But it's worth it.
If a drought is coming along, then yes.
So this must be useful when there are actual droughts out in the world.
I think that's what the authors are hoping. Obviously, this hasn't been tried outside yet, and it's mostly early days. But this sort of approach could lead to much higher yields in water-poor years. Drought is one of the leading causes of crop loss globally. And the trouble is, whereas we can predict the weather next week, we might not know that in a year's time there's going to be a massive drought.
Yeah, and next week even is a bit of a toss-up. Do you think, in theory, you could just spray this on your crops? How long would it protect them for?
The initial work in the paper shows that if you spray a high concentration, you will maintain an abscisic acid-like response for 5 days. Now, I don't know how long after that it would carry on doing it, but the idea that you spray it before the drought and you get the plants prepping first might make a big difference in survival later on.
And will this work for any plants?
It'll certainly work for the crop plants that they've tried it on. I think it'll work for most plants because water relations are so integral to colonizing land. Abscisic acid seems to have evolved a long time ago, so nearly all plants respond to abscisic acid.
Just like they'll respond to this new thing.
Exactly.
Well, with growing water demands, if that chemical can be rolled out, it could have a brilliant impact worldwide. That was Jim Rowe from Cambridge University, and you can find the research paper describing the spray-on drought-resistant chemical in the journal Plants Biology. The study was done by a team of scientists led by Sean Cutler.
And if you'd like to follow up on any of the other stories that we've been discussing here on The Naked Scientist this week, you can find the references and write-ups for them on our website. That's thenakedscientist.com. Well, now let's head over to the mailbox. This is where we read out some of your correspondence. We've heard from Kay. She's in Australia and she's written in with her own theory about dark matter. She says she thinks it's really... she thinks it's just all those lost black socks that have disappeared from the world. They had to go somewhere. You're an expert on that, Izzy. You actually looked at the maths of lost socks earlier this year.
Yes, well, I was thinking that as I was hanging up my washing today. I had 3 different black socks, none of which were in a pair, and so I'm right with Kay on that one.
Well, she says, of course, no one can see the dark matter because no one can find the dark socks. But Rob Eastway, who's the mathematician, told you that the solution to the black sock problem is just to buy exclusively black socks, and then you never know you've lost them.
Well, absolutely. Or check the weird little filtration part of your washing machine, and they might be there, but don't go around disassembling your washing machines, is my advice. And listener John has a correction to our piece last week about the nano guitar string. In the piece, it was wrongly said that Jimi Hendrix used feedback by moving his guitar towards a microphone, whereas he actually just moved his guitar, which is a microphone of sorts, towards the amplifiers. Thanks for pointing that one out.
So if you have any comments, feedback, criticism, or suggestions for the programme that you'd like aired on the mailbox, you can send that in now. It's chris@thenakedscientist.com, or you can tweet at Naked Scientist. We've also got our Facebook page, of course. You go to facebook.com/thenakedscientist and we'll pick them up.
Music in the programme is sponsored by Epidemic Sound, perfect music for your audio and video productions.
The Naked Scientists podcast is produced in association with Spitfire, cost-effective voice, internet and IP engineering services for UK businesses. Find out how Spitfire can empower your company at spitfire.co.uk.
Now this week we're diving into the bins and rifling through rubbish because we're trying to figure out what is going on in the world of recycling.
The average Western country produces far more recyclable waste than it can deal with. And ever since China stopped importing most types of waste last year, we've seen crisp packets and margarine tubs piling up in illegal dumps in countries like Malaysia. So what is going on? Is our recycling system still working? And what does the future hold?
Before we get into that, though, we've got to start at the individual scale. Now, when I put something in my recycling bin, where does it actually go? Well, to tell us, here is Bryony Rothwell. She's the Partnership Manager for ReCap. They're an organisation that coordinates waste right across Cambridgeshire.
Now, we've been told that most things can be recycled. So I've been shopping, and Bryony, I hope you can tell me where some of these things will end up if I recycle them. So first up, we've got a milk bottle here, and that's made up of a hard plastic. Is that a problem?
No, this is a very recyclable material. It's a plastic called HDPE and it's recycled in the UK back into milk bottles. There's a very good recycling system for that material, as long as it's presented in your curbside bin clean, washed out and squashed with the lid back on. Other materials such as cardboard, if it's in good quality, not contaminated with food, that will go on to be made into more cardboard, which will be made into packaging for cereal. Anything that's presented in your recycling bin in a high quality way, so it's not wet, it's empty, it's clean and squashed, it will get made back into recycled products.
So why is this idea of it being clean so important?
Any contaminant that goes into the recycling bin, so that be liquids or food, can spoil the other quality of the materials that are in that curbside recycling. And so when it goes through the process and the reprocessors get it, the more they have to remove the contaminant to actually get the quality of material to recycle into a new packet. Anything that's food that's adhered to that container or box either spoils the box if it's cardboard, or it means they've got to wash it more. So it just takes longer and costs more money, and it doesn't make it viable.
Right, I see. And finally on my shopping list is also a bag of pasta. I get through so much of it. And it's come in this quite flexible wrapping. So where does that end up?
Unfortunately, these usually are bags of composite laminates, and the type of recycling that they would need to actually separate the plastics out is very complex. And unfortunately, at the moment, we aren't able to do that. So they often will just go into the grey bin instead of your recycling.
Just wondering, Bryony, because this sounds wonderful, and I'm quite surprised to learn quite how much of the material is recycled, as you were just saying to Izzy there. But of all of the rubbish, and we must have some idea as to how much rubbish is being generated, what fraction currently is going the right way and is turning back into new milk bottles and so on?
In Cambridgeshire and Peterborough, we have a recycling rate of 59% across all the local authorities. So
is that high?
That's a reasonable amount. I mean, national average is around in the mid-50s.
Indeed, because looked at another way, if it's a 50% recycling rate, this milk bottle of Izzy's here, that means that for every two of those that get made, one doesn't end up in landfill, but one does.
Unfortunately, yes, that is the case. And there is a lot of material in our residual bin still that can be recycled that isn't being. So there's about 10% paper in Cambridgeshire that's not being put in the recycling bin, about 10% plastic. A lot of the heavy materials are coming out, so glass and metal we seem to be extracting from the bin. But there's about 30% food in your grey bin as well, which could be composted, but people are just putting it in landfill at the moment.
Oh, right. So included in your figures for what we're calling recycling includes stuff that could go in the compost heap?
Absolutely.
Because I traditionally regarded recycling as physicals like plastics and cardboard. So that's interesting.
Anything that's contributing to obviously reusing materials, then if we can reuse that food for conditioning for the soil, then making it into compost is a better use of it.
There's obviously a cost to recycling as well as a cost to manufacturing from the get-go. And in order to make people use recycled things, it's got to be both economically and energetically favourable. There's no point in recycling things for the sake of just recycling and actually doing more damage to the planet. So how is that calculation made?
So for things like your plastic bottle, 50% less energy is needed to make a recycled bottle compared to a virgin plastic bottle.
That's quite high.
That is quite high, yes. So it's really worth putting your plastics in your recycling bin in the right condition.
So are there any materials then for which the equation is less obvious or for which it's less beneficial? But what about things like glass?
Glass, again, highly recyclable as a product, and metal likewise. The difficulties come with things like cardboard, paper, where you get contamination and you have to take out that material, and it's more sorting and sifting to get the clean product through.
One of the key things about this whole recycling process, though, is you've got to have end-user engagement. It's all down to, and it's very dependent on people like me participating actively and proactively putting stuff in the right bin, isn't it? So as a member of my family said to me today, when I said we were going to come and talk to you about recycling, and she said, why is there no machine that could just take a bin and sort it all out? Problem solved.
Well, a lot of the waste that goes into the blue bin or the mixed recyclables is sorted by machine at the other end. Unfortunately, the best recycling rate in the world are usually where the human beings sort it before they put it in a bin. Wales is the third highest recycler in the world, and they have a curbside sort process that means that human beings have to put it all in the right bin before.
Very expensive, though.
Very expensive, unfortunately, but that's one of the things that the new resources and waste strategy is looking at, is whether local authorities should move to that kind of system.
Bryony Rothwell from Recap, thank you very much indeed. Now, Izzy's got one thing left in her shopping bag. Izzy, you are a bit fond of cats by the look of things. There's some cat food in here.
Yes, if anyone goes on my Twitter, you'll just see constant photos of my pets. So the final thing on my shopping list is a pouch of cat food. I can't put this in my blue bin, even if I wash it out, because it's not made purely of plastic. Instead, it's a plastic aluminium laminate. It's a decent material environmentally because it's so light compared to aluminium, so it saves resources and fuels when transporting it. But until recently, it couldn't be recycled at all.
It's very similar, isn't it, to these packet drinks as well, which are almost the same shape. It's almost like they've started to put cat food in a packet drink packet, isn't it? But you know what I mean? They're those foil pack things. And these are these aluminium laminates, which previously have been a big headache to recycle. But actually, this is all going to change because there's a company called Enval, and they've developed a process that can separate the plastic away from the aluminium, and they say they can then recycle both, and this will hopefully get to the bottom of some of the challenges that Bryony was just talking about. Phil Sampson went to visit the plant and to meet Enval's CEO, his name Carlos Ludlow Palafox.
We have baby food pouches, we have paint tubes, we have sachets, bags for instant coffee, pet food pouches. Plastic aluminum laminates are being used for all sorts of products, and what we have managed to do is to create a process that actually renders these things, plastic aluminum laminates, recyclable.
Before they weren't recyclable?
Before they weren't recyclable. We separate plastic from the aluminum. It's a chemical separation in the sense that we pyrolyze the plastic. Pyrolysis is a process where you have something that could burn, but you apply that energy in the absence of oxygen. Therefore, that something that could burn doesn't burn because there's no oxygen. It just degrades into other things. In the case of a plastic, if you pyrolyze a plastic, you heat it up to very high temperatures, in this case around 600 degrees. And because the plastic came from oil in the first place, what we do is to produce an oil similar to what you have in crude oil. So you are turning back plastic into its original crude oil. We feed the packaging into the shredder. All the pouches, sachets, tubes, etc. get shredded into flakes. and that goes into the oven. We use microwaves to heat up the reactor where the reaction takes place.
Microwaves.
Microwave-induced pyrolysis, correct.
Gotcha.
And now some of the listeners, I'm pretty sure, will think, how on earth are you heating up plastics using microwaves when I know that if I put a plastic dish with soup in the microwave oven in the kitchen, the soup heats up, but the plastic doesn't. So how do we do it? Well, we heat up carbon with the microwaves, and once that carbon is hot, then we start the addition of material.
So the microwaves don't actually heat up the thing that you're changing?
Correct. So the microwaves heat up carbon, and then the carbon transfers the heat by conduction to the material, the plastic. The plastic pyrolyzes. The gases that are the pyrolytic gases escape the reactor, and we cool them down. About 75% condense into an oil, and around 25% of what was plastic remains as a gas, and that gas we feed into an electricity generator that then feeds the microwaves to produce the energy that we need for the process.
So you can use only a quarter of the petrol product, basically, to power the rest of the plant?
Correct. The aluminum, on the other hand, it forms flakes that then we melt and form ingots.
So all this that Carlos is describing happens inside a big industrial building where Enval has set up their plant. So I asked him to show me inside. Wow.
Well, this is it. This is where the magic takes place.
It's really, really big.
For a pyrolytic process, it's actually quite compact. That big box, for all practical purposes, is a very large microwave oven. Much larger than the one that you have in your kitchen, 2 by 2 meters. And more importantly, in power, is 150 times more powerful than a house one.
How long would it take to heat up my soup in one of those?
Less than 2 seconds.
By the way, what is that smell?
It's the smell of oil.
Not that I'm not impressed, but let's get out of the noise and the smell. Back outside, Carlos shows me some of the end product of the pyrolysis, pure flakes of aluminium, or at least as pure as when the laminates were first manufactured.
Lately, what we have done is to actually do the melting of these flakes into ingots, like this one that I'm holding in my hand. It's much more valuable to sell the aluminum as ingots than is to sell it as flakes. The oils is also a very valuable product, and we sell it as heating fuel. But one of the plans that we have is to use the oils for the production of virgin plastic. So full circular economy for the plastics as well, not only for the aluminum.
Where does a company like you fit into the way that recycling works in this country?
Excellent question. Recycling is a very complicated world. When a new material comes out, the waste sector normally is very slow reacting to those kind of things. What tends to happen is that companies that develop recycling processes need to prove over and over again that it actually works before the large waste handlers actually want to engage. We recently decided that we're going to stop wasting time waiting for large waste handling companies to buy plants from us, and we're going to put more plants ourselves.
But if it's the waste operator's job to recycle stuff that can be recycled, why aren't they just picking this up?
Well, it's very complicated because some of the contracts between the waste contractors and the local authorities or the county councils are insanely long, 20 years long. And the waste composition of 10 years ago has nothing to do with the waste composition these days because brands change the kind of packaging that they use. So you say, well, they have a duty to collect and recycle. Yes, from a certain point of view, when that duty is established in a contract. But if a new material comes in the middle, they have absolutely no duty to collect absolutely anything. Even worse, they have no incentive whatsoever. Because for a waste handler, whether a pouch of baby food gets collected or gets landfilled makes zip difference to them because they get money either way.
You're joking. There's no incentive for them to recycle something.
Not necessarily for the waste handlers. A lot of the waste sector, the traditional waste sector, says, why do we bother doing more complicated operations if we can just carry on pushing stuff in the ground? So unless they are forced to do it, they won't do it.
I find it quite shocking that it's not as simple as if you can recycle something physically, then you just whack it in your blue bin and it'll get to the people who can recycle it.
No, it's really, really not that simple. Sometimes it has nothing to do with the materials.
So what's it like being in this industry?
It is fascinatingly chaotic.
That was Carlos Ludlow Palafox from recycling company Enval.
Now, this week we're looking at recycling and what we can and can't recycle, and how policy needs to change in order to help us do it a bit better.
Well, recycling isn't just a technological problem, it's an economic one as well. At every stage, from us washing out our juice cartons to waste management companies selling great bales of recyclable plastic, it comes down to incentives. Like Carlos has just said a moment ago, it is fascinatingly chaotic. And some people are sceptical about whether it even works. Roland Gaia is one of those people. He's a professor of industrial ecology at the Bren School of Environmental Science and Management in California, and Adam Murphy had his opinion on the state of recycling.
The only environmental point of recycling is to displace primary material production, which means that turning scrap into secondary material needs to be cost competitive with primary material production, and also the secondary material needs to have technical specifications that are similar or ideally equal to those of primary material. For plastic in particular, the economics of plastic recycling simply don't work. And you could say it in two ways. You could say plastic recycling is too expensive, or you could say virgin plastic production is too cheap.
Does that mean as well that when you use something for plastic and you recycle it, it has to be used in something of lower quality at the moment?
Very often that is true, yeah. It is not necessarily true, but in practice right now, the way we design our products makes it difficult then to get a clean single polymer stream of recycled material. The way we use it and collect it, it becomes contaminated. And plastic is a vast group of very different materials. So if you want to recycle plastic, you actually need to separate the different polymer types.
Why is it then that recycling doesn't reduce the amount of primary material that we use?
Unfortunately, there's not just a single reason, there are actually several reasons. First of all, if you want a competitive recycled secondary material, you have a couple of hurdles that you have to take to get to that point. You need a well-designed collection system that allows you to then separate the polymers and keep contamination to a minimum. The next hurdle is you need good recycling technology. So you need something that really works for the type of scrap that you've collected. The next hurdle is that you actually need a market for your secondary resource that you just generated. There are many recycled plastics that are not very desirable, so no one really wants to use it to put it into their products. And to make things worse, even if you have a fairly desirable secondary material, there is no law of nature. Physics doesn't say that if we increase our secondary plastic production, primary plastic production has to come down, right? This is a market-mediated effect.
If when we recycle something we introduce impurities and we keep recycling, doesn't that mean even with the best of intentions, everything we have is going to end up in landfill eventually?
Every single unit of material that we produce will become waste. It's literally impossible to keep material in circulation forever. And the buildup of contaminants is one of the reasons why I firmly believe that the best you can do is get multiple cycles out of a material, but it's not even clear how many exactly. In fact, with plastic, we studied globally the circulation of secondary plastic. We think that the vast majority of recycled plastic gets exactly one additional cycle, and then it becomes basically waste the next time around.
So given all that, what do you recommend we can do going forward?
I think we need to be more honest about what we would need to do and what kind of systems we need to establish if we really wanted recycling to work. And then the other thing, I think, which is at least as important, is that we do need to remember that in a hierarchy of pollution prevention approaches, recycling is only the third best, right? There's reduce, reuse, recycle. So recycle is third. So really, if you have a reusable cup rather than a single-use cup, then you get many, many, many uses out of that particular piece of plastic rather than having to recycle, trying to build a system that is able to recycle the single-use cup. People think that it's mostly an engineering and a technical issue, and I've come to the conclusion that it's actually mostly a social issue. By treating recycling mostly as a technical problem, we'll never quite come to the point of making it work. I think we need to start recognizing that the social dynamics of recycling are at least, but probably even more important than technology and the science behind it.
It's thought-provoking stuff, isn't it? Roland Geyer there. He's from the Bren School of Environmental Science and Management at the University of California, Santa Barbara.
Obviously, we shouldn't just stop recycling. So what can we do? With us now to help untangle all of this is Margaret Bates, Professor of Sustainable Waste Management at the University of Northampton, who describes herself as, and I love this, obsessed with anything waste related. Margaret, we thought you'd be the perfect person to ask. What do you think of what we've just heard? Is Roland right that recycling economically isn't really working?
I think it is working. The economics aren't necessarily the most important thing. The carbon benefits, the impacts on climate change are hugely important. I totally agree with him that the social aspect's really important as well. People buy something, use it, and then go, why can't I recycle this? Whereas actually we need to have the situation where when you're buying something, you factor into its end of life at that point. Comments were made earlier about our infrastructure really hasn't kept up, and it hasn't. Changes in waste over the next 20, 30 years will need an investment of about 35 million. And to be honest, when we're talking about big waste handlers, they don't really exist anymore. They're resource management companies. They spend a lot of time and effort in making sure that the way we collect things is the best way to recover the value as much as possible.
Margaret, can I put something to you? Because I was cleaning my teeth today, and yes, indeed, my dentist would be delighted. Well, actually, maybe not, because it means I make fewer visits. But I bought myself a number of years ago an electric toothbrush, and I've been delighted with it. It's lasted 8 years. But now I've got to the stage where the battery has clapped out. It doesn't survive more than 2 nanoseconds away from the base station charging, and I'm going to have to throw it away. What infrastructure is in place to recycle gadgets like my toothbrush?
There are a number of sort of high streets where you can take your electricals to be recycled, or you can look on Recycle Now, which will show you where you can recycle materials. But you don't necessarily need to buy stuff. So perhaps there's an opportunity to have a leasing model on a toothbrush where you don't buy it. They still own it, and then when you've finished with it, you give it back to them and they swap it for another one that might be repaired or refurbished or just have a new battery in it.
I take it you're referring to the body rather than the brush head. You wouldn't want a second-hand one of those, would you, Margaret?
I really wouldn't want a second-hand one. I'm not sure I want to use mine twice.
No, I mean, the cynic in me is thinking, is this engineered obsolescence to make sure I go and buy another toothbrush? Because it's not in the manufacturer's interest, is it, to make something which, if it works too well and lasts too long, they can't sell me another one. There's always going to be that tension, isn't there, with industry, where they want to make something that lasts a certain time, which incentivises you to go and buy another one.
But that's why we need good policy, good what's termed extended producer responsibility. So it incentivises things that last longer, that are easier to repair, and then easier to recycle at the end of their life.
What fraction of goods and products are currently being built or designed with their end of life in mind at the outset?
We have absolutely no idea, really. End of life isn't a factor in the manufacture. We're getting better. So if you look at plastic bottles, for example, the average recycled content of a plastic bottle is about 15%, but that's going up, and there are government plans to tax people extra if they don't put a minimum of 30% recycled content in.
Have they actually gone in further up the food chain, as it were, and said you can't design stuff before you've come up with a valid plan for how you're going to deal with it when it's died?
That's what the extended producer responsibility legislation's about. But interestingly, as a householder, we don't have that. So there's a system called Pay As You Throw, where every wheelie bin produced in Europe since 1996 has a microchip housing in it. And in many countries, householders are charged proportionate to how much waste they produce. Whereas you and I can throw away as much as we like and still pay the same amount of council tax.
Bit dodgy that, though, isn't it? Because it incentivises people to either fly tip or go and chuck it in someone else's bin, and then your neighbour ends up paying for your rubbish, don't they?
Well, no, not really. I mean, if they put the price up of your shopping, do you start shoplifting? Most people do the right thing and will try and change their behaviours to make sure they carry on doing the right thing. And this is really common throughout Europe and other parts of the world. Even tried it recently in Guernsey, and it's reduced the amount of waste people produce. And that's what we really need to look at. We focus very much on recycling. Recycling isn't the top of the best things we should be doing. It's not even the second. So we should be reducing the amount of waste we generate. And sadly, charging people proportionate to how much waste they produce is one of the good ways of doing that.
I think the most poignant point that Roland Geyer made when Adam spoke to him was to say that there are lots of people who think they're doing the right thing by going and buying stuff that's labelled up recyclable, but just because it's recyclable, as Brian is saying, it doesn't mean it gets recycled. And so really what we need to do is to shift the mindset of people onto making that demand for things that have been recycled, not just are recyclable.
Yeah, we need to start off by not buying things we don't need. If we do buy stuff, we need to make sure it's got a high recycled content. Then we need to reuse it as much as possible. And then when we've run out of any use for it, then recycle it. So it's part of looking at the whole life cycle of how we interact with our stuff.
Wonderful point to finish and some sage advice. Margaret, thank you very much. That's Margaret Bates. And before her, you heard Roland Geyer, Carlos Ludlow Palafox and Bryony Rothwell.
And we just have time for question of the week. And this super cool question is from listener Mike.
When the outside temperature is hovering around the freezing mark, the condensation or dew on my automobile windshield is in a liquid state. But if I wipe the windshield, the liquid water changes to ice. Why is that?
It can be a real pain. One moment you're just wiping your windshield on a cold morning. The next, you've got to go about taking all the ice off. But what's going on? I reached out to Liz Thomas, paleoclimatologist at the British Antarctic Survey here in Cambridge, to find out.
This is the result of a phenomenon known as supercooling, the process of lowering the temperature of a liquid below its freezing point without it becoming a solid. This happens because they lack something to start the freezing process, called a seed crystal.
This can happen to water bottles too. You can put them in your freezer and they won't freeze. That is, until you give them a knock.
On a cold morning, when the temperatures are close to zero, the water vapour in the air, or the dew in your windscreen, is in this supercooled state. The action of spreading the supercooled droplets over the cold surface of the windshield turn the water vapour into ice. This is because the windshield is generally colder than the surrounding air.
Sloshing the water around on your windshield then makes a point the water can freeze from. So you're a superhero. You can turn water into ice with just your hand. But it's not all so chill.
Another example of supercooling is freezing rain. In this case, the rain droplets become supercooled in the upper atmosphere, but remain as supercooled droplets until they reach the Earth's surface, where they turn into ice. This can be a real problem for aeroplanes, where the ice can build up rapidly on the wings and make flying incredibly dangerous.
And as Alan Calvert pointed out on the forum, supercooled water can freeze in seconds. So thanks to Liz Thomas for giving an answer to such a nice question. Next week, we're answering this one from Vinny.
I have read mosquitoes have a preference for blood type and prefer people with type O blood over those with type B, but prefer type B over type A. Is this true? And how do they know the difference between types?
Well, if you can answer Vinny's question, email chris@thenakedscientist.com, find us on Facebook, tweet @nakedscientists, or join in the debate on our forum. That's thenakedscientist.com/forum.
That is actually a very good question, isn't it? How does a mosquito know your blood group before it bites you?
I definitely now want to know, and what is my blood type? Oh my goodness, I'm overthinking everything.
That's it for this week. Thank you very much to Phil Sansom, who put the programme together. Do be sure to tune in at the same time next week when it's Q&A time. This is where you ask the questions and we put them to a big brain panel of people who will answer them for you. If you have a question, speaking of which, you can send it in now. It's chris@thenakedscientist.com. Don't forget, we do have our donation drive running. We do have a target we have to try and reach. And if you can help and you enjoy this programme and you tune in each week, and we know there's a lot of you, we would ask you, please do support us with a modest donation. We've made it very easy, very safe and secure. You go to nakedscientist.com/donate. The Naked Scientist comes to you from Cambridge University and is supported by the EPSRC and Rolls-Royce. I'm Chris Smith. Thanks for listening. Until next time, goodbye.